Hi there, Physics 30. I'm just going to explain to you how Unit D, Lesson 2 lessons can be discussed over a video now. So first things first, I'll show you my screen where I'm dealing with this first topic here, 16.1, the nucleus. So keep in mind, it's going to be dealing with nuclear reactions throughout this whole unit due to the fact that it is looking at how we can look at physics in a different perspective of things compared to classical physics. So with this, we always want to look at what the nucleus is all about. So which elements are these? So we always realize in the diagram that I have to the right here, you'll have your protons being red and your neutrons being white. So here's an example of carbon. Both have 6 protons. And if they have an atomic number of 6, that would mean that there's 6 protons that are available and even 6 electrons zooming around it. It's not an isotope. So what is an isotope? Let's quickly recap what that is all about. So isotopes are basically chemical properties, but different physical properties, such as they have behaving in nuclear reactions and how their numbers of neutrons change. That's the biggest thing here to actually realize. Anytime you have atomic mass, and you can actually figure out how many neutrons exist in each of the problems. So with that, in fact, let's take a closer look at carbon 12 and carbon 14. In carbon 12, you will realize that's the mass number 12. That's on the top left-hand corner of the element, or atom, I should say. So in there, you will have the same amount of protons regardless. Protons never change. How do I know what the proton is? Well, this is where you would have your actual periodic table to help you on that, plus the fact that's what your number at the bottom left-hand corner is all about. So with that in consideration, you will realize 12 and 14. The top left-hand corner is saying 12, so that's the atomic mass number. How to figure out an atomic mass number? You basically take the protons and the neutrons. So currently, there must be 6 neutrons for this carbon element due to the fact of this is your proton, 6, plus another 6 will make your 12. So that's what this is coming from here. Over here at carbon 14, you will realize that you would have a combination of protons and neutrons to make 14. So you have 6 protons. So what plus 6 makes 14? You will realize it will make 8. That's your neutron number. So that's one of the things of isotopes. So keep in mind, I have the following information here. Number of protons plus number of neutrons will give you your mass number. So atomic number is your number of protons. With that, in fact, let's move on. Let's look at another example. And in this case, let's look at hydrogen 1. And hydrogen 1, so that must mean there's an atomic number of 1. And then the proton is 1. So that means there's only 1 proton and no actual neutrons in this case, because of the fact that it has the same number. Okay, let's look at hydrogen 2. So what ends up happening in this case is that it has 1 proton and 1 neutron. Let's look at the next one, hydrogen 3. In hydrogen 3, you have 1 proton, that's what that bottom left-hand corner means. Add 2 to it, you have 2 neutrons, hence the fact the colors I'm using here, green colors for the neutrons. With that, in fact, let's look at another isotope of lithium now. So in lithium, we have top corner number is 6. So this means that a combination of protons and neutrons will give us 6. Currently, we have 3 at the bottom, so that means that's the actual number of protons. So that means we have 3 neutrons, hence the fact 3 red, 3 green. If we take another example of lithium, isotope is lithium 7. So that means 7 represents the whole fact of numbers of protons and neutrons. Add them both. From 3 plus what makes 7? As we realize, that's 4. So that means there's 4 neutrons in lithium 7. If we move on to the following practice problem, how many neutrons are in a nucleus of 24, 12 magnesium? So how do we actually pronounce this? Magnesium 24. So first things first, as we said earlier, we are going to realize the 24 represents both protons and neutrons. Okay. So in that case, what's going to happen is that you're going to know the number of protons already, because that's your 12, plus question mark equals 24. Well, that should be straightforward. You're going to get 12 neutrons end of the day. Notation for that is NO, a superscript of NO, by the way. Okay, the next one we're going to look at is this whole fact of reading it. Find the atomic mass number for a uranium atom that contains 92 protons and 146 neutrons. So as we said earlier, to figure out the atomic number, we have to add protons plus neutrons. So that means, according to this question we have here, it's 92 protons plus 146. Add those both together, you're going to get your number. And if you do your math correctly, you should get 238. So with that in fact, how about I'll give you a moment or two to complete the following yourself, or I will stop for a second here, and then you could try the following. So there's 4 questions you need to try here. How many protons and neutrons do each of the following nuclei contain? So keep in mind, protons and neutrons you need to figure out. Protons is the easy one, but the neutrons you might have to do a little bit of math there. Give you a second here to try that. Another 30 seconds I'll give you. Okay, let's start off with A here. So we are looking for strontium 38, 90. So what ends up happening is, keep in mind, the atomic number is 90. Sorry, the atomic mass is 90. 38 is the actual how many protons there are. So we know there's 38 protons currently, plus number of neutrons, which is question mark, will give us 90. So what we need to do is just do some simple math here, and we can actually figure out how many neutrons there will be. So 90 minus 38, we should have the ability to figure that out. 90 minus 38, we get 52. So that would mean there is 52 protons, sorry, 52 neutrons to in this question. Here are our answers. In letter B, we have carbon 13. So what ends up happening in that case, we know there's 6 protons plus question mark, or you could say any variable if you like, or neutrons, will give us 13. So that should be straightforward math there. You will realize 13 minus 3 would give us this whole fact of 7 neutrons. If I scroll down to the next one, we have iron 56 and then hydrogen 1. So let's first start off with hydrogen 56. Letter C. So we know there's 26 protons. That's what that bottom number means. Plus question mark gives us 56. Now if we do the math in that case, we're going to be realizing we're going to have How many neutrons? Well, 56 minus 26 should be 30. 30 neutrons. And then the last one with the hydrogen, one proton plus question mark should give us 1 again. So in that case, what do you have? 0 neutrons. Okay, hopefully you did give that a try before I gave you the solutions there to help you. With that in fact, let's scoot on over to the next section of determining how heavy these actual subatomic molecules are. So first things first, we're going to have to understand that the charge of an electron is the following: 1.6021177 times 10 to the negative 19. The mass is dramatically small for our electron, 9.109383 times 10 to the negative 31, as the actual mass written with the U here is 5.485799 times 10 to the negative 4. So same thing forward with proton and a neutron. Very interesting to see the neutron's charge is actually neutral, so that's why there's no charge. It's blank as 0. And it's the exact opposite of an electron and a proton. The masses, you will realize, are dramatically a little bit bigger than the mass of an electron, but it is bigger. So with that in fact, let's look at the next practice problem and see if we could actually tackle it. Okay, calculate the gravitational force that 2 protons exert on each other when they are 5 meters apart. So, gravitational force, we've learned back in physics 20, is dealing with Fg equals to mg. So, we know this little f, as we've learned earlier, is a femto. So it's a very small unit. And we also know that gravity always takes a part from this. Give you a try. I'll get you to try it first to see what you get. If you're not getting it, give me a moment and I'll show you the solution. Could also think of the formula we've used in physics 20. Fg equals to the constant of g, mass 1, mass 2 over r squared. And I would probably encourage you to use that one because of the fact of we have 2 masses of a proton and we know the radius of it, which is 5 fm. Once again, and F is times 10 to the negative 15. Okay, so let's get to it. First of all, the constant you've learned back in physics 20. There we go. 6.67 times 10 to the negative 11. Mass of 1 handy-dandy proton is 1.672622 times 10 to the negative 27. What I'm going to do is square that number because you're just going to multiply twice by itself. And then the radius is, as it said, 5 fm. So 5 times 10 to the negative 15. Once you type that in your calculator, you're going to get how many significant digits? Only 1 because of 5 fm. 7 times 10 to the negative 36 neutrons. So that's how you would actually tackle a question like this. So we've learned FG back in Physics 20, but keep in mind, everything you've learned in the past will be used in this course, as I said from day one. So let's move on to the next question. Right here. Calculate the electrostatic force that two protons exert on each other when they are 5 meters apart. So if we're dealing with electrostatic, we should be using the whole fact of the formula we learned this year, Fe equals to K, which is a constant, Q1, Q2 over R squared. So with that in fact, let's do the same thing as we did earlier. So the second part of the question, number 2 here. So electrostatic, so we're using Fe equals to K Q1 times Q2 over R squared. So our constant is 8.99 times 10 to the 9. You're multiplying it twice with the same number. And the number we should be using is an electrical force. And that charge of a proton is 1.602177 times 10 to the, if I could squeeze it in here, negative 19 squared. And then over 5 times 10 to the negative 15. Keep in mind, femto means that you're going to get one significant digit answer, and it should be 9 newtons. So once again, keep in mind, Fe, we've learned that back in Unit 2, where I got that from, or Unit B. So with that in place, what else we could say about this? The strong nuclear force. Using accelerators, scientists have discovered the forces that hold nuclei together is an essential bit of this other force that we brought into this course, or as a force as Newton indicated back in the day. Another thing, nuclear forces act over very small ranges. So in that case, over 100 times greater than the electrostatic force. We also know that the strong nuclear force is independent of the charge, and the attraction is small. So because of the fact that when you subtract both protons and then neutrons, regardless, you're always going to get a small amount between each other. And the last thing I wanted to talk about, why is unstable nucleotides. Unstable nucleotides tend to disintegrate, causing a different nucleotide is to be produced, energy to be released as radiation. And unstable nucleotides have too few neutrons in relation to the number of protons. And when that does happen, they're not going to be stable. So in general, the more protons in the nucleus, the more neutrons that are required to overcome the electrostatic. It's one of the important things for why it happens. All elements with atomic number greater than 82 exist only as unstable nuclides. If there's any further questions you would like to talk about in this unit, do not hesitate to let me know. Otherwise, have a great day.